Software evolves constantly. Every patch, refactor, or bug fix carries the inherent risk of a regression. How do we mathematically guarantee that a change preserves the intended behavior of callers without re-verifying the entire codebase? Regression verification addresses this, but it faces a brutal trade-off. Existing techniques either require expensive whole program reasoning that doesn't scale, or they rely on manual specifications that rarely exist in practice. Today, we're exploring a breakthrough approach that bridges this gap. We're looking at sound, modular regression verification driven by large language models, but with a twist. You don't need a full behavioral specification. You only need a partial, caller-sufficient contract. This is based on the paper, Partial Contracts Suffice, Sound LLM-inferred Regression Verification by Charalambous and colleagues from the University of Manchester. We'll dive deep into the relational semantics, the soundness theorems, the LLM-inference loop, and the evaluation results that show this approach achieves verification rates comparable to state-of-the-art tools while certifying a stronger safety property. Let's start with the problem space. We model each version of a function as a relation from input pre-states to output post-states. If we have an old version F1 and a new version F2, we want to check if they are equivalent. But full input-output equivalence is often too strong. A developer might legitimately change behavior on paths that were already buggy or undefined. We care about preserving the behavior that callers actually rely on. This leads us to conditional or regression equivalence. We fix a property phi, marking the behavior worth preserving. We ask for agreement only on inputs where the old version already satisfied that property. Where the old version violated the property, the new version is free to differ. That freedom is exactly where a bug fix lives. To make this scalable, we need modularity. We can't reanalyze every callie at every call site. Instead, we abstract each call against a summary. The abstraction must be sound, meaning it overapproximates the callie, admitting every behavior the function can exhibit. The authors propose using a function contract as that abstraction. A contract is a horse-style triple. A precondition requires, a postcondition ensures, and a frame clause assigns naming the locations the function may modify. The frame clause is critical. It tells the verifier which locations are snapshotted before the call and asserted unchanged after. Without it, the verifier must havoc every reachable location, making the abstraction too coarse for a useful proof. Now here is the core insight. Contracts like this are almost never written by hand. The authors infer them using a large language model, but they never trust the LLM blindly. The LLM proposes a contract, and the verifier enforces it against the old version. Only an enforced contract is used. A wrong guess is rejected, not believed. The pipeline works as follows. We take the old version F1 and the new version F2. We infer a contract C for F1. We enforce C against F1, proving that the function's relation is a subset of the contract's admit set. Then in the regression check, we replace every call to F1 with the contract C. The new version F2 runs concretely. We check that the outputs agree on the slice of behavior the caller observes. This is a one-sided abstraction. We only abstract the old version. The new version is analyzed concretely. This is sound because the contract overapproximates the old version, so if the abstracted check passes, the real check must also pass. The paper formalizes this in Theorem T1. The theorem proves that a one-sided contract suffices to prove property-relative regression equivalence, provided two conditions hold. First, enforcement. The contract must overapproximate the old function. Every run of F1 must be permitted by the contract. Second, sufficiency. For every input in the scope of the property, every output the contract allows must satisfy the equivalence obligation against the new function's output. Condition 1 makes the proof sound. Condition 2 is where the contract must be tight. Crucially, the contract only needs to be tight on the behavior observed by the property. Off that slice, it can stay weak. This looseness is what makes the inference tractable. This leads us to the concept of caller sufficiency. A partial contract pins down exactly what the caller reads and stays silent on everything else. Consider this example. We have a function shrink that trims a box. The old version has a bug. It forgets to shrink the height. The new version fixes the height. A caller usable width only reads the width. If we check full equivalence, the fix is flagged as a difference because the height changed. But for usable width, nothing changed. A partial contract can pin the width and leave the height free. The regression check replaces the old shrink with a contract, runs the new shrink concretely, and compares only the width. The check passes. The fix is accepted. The system implementing this has three components. Contractor parses the C project and scaffolds harnesses. Scrib-E runs the LLM-based contract inference loop. Regver discharges the regression check. The inference loop is driven by counterexamples. When the verifier enforces a proposed contract and the frame check fails, the model checker recovers the offending right from the counterexample trace. Scrib-E feeds that trace, not just a failure flag, back to the LLM to refine the contract. This is counterexample-guided inductive synthesis. The authors evaluate three models, Opus, Kimi, and Qwen. They find that model checker counterexamples alone provide a highly effective refinement signal. On the Frama-C problem's benchmark, Scrib-E reaches verification rates comparable to tools like AutoSpec and Pregus, which rely on weakest precondition reasoning or value analysis. Most contracts converge after a single refinement iteration. But does the partial contract lose us anything? The paper introduces a tool called Judge, a semantic comparator that decides contract subsumption by checking set inclusion on admit sets. Judge can tell us if one contract is strictly tighter than another. The results are striking. When the authors take the inferred partial contract and strengthen it through additional rounds, the tightness saturates almost immediately. For the vast majority of targets, the partial contract is already as tight as the loop can make it. The partial spec stopping point costs almost nothing. Caller sufficiency captures nearly all the attainable tightness. This validates the theoretical claim that we can stop at caller sufficiency without sacrificing proof power. A looser contract admits more behaviors, potentially causing spurious divergences. But since the partial contract is already tight on the observed slice, we avoid those spurious alarms. Now what about scaling to nested calls? The authors introduce a depth-bounded contract closure. We infer precise partial contracts for functions within a configurable depth, n, from the target. Functions at depth, n, receive boundary contracts that havoc the entire footprint. Functions beyond n receive no contract. This bounds the verification cost independently of the full Kali depth. The soundness theorem extends to this closure via induction. The boundary contracts trade precision for scalability, but they never break soundness. The authors evaluate soundness on ECBenchC, a suite of program pairs labeled for equivalence. They run the regression check in a portfolio mode. First, a contract-free baseline runs. Pairs it cannot decide are escalated to the contract-based arm. The results are robust. On the decided pairs, the system never fabricates an equivalence. 0 false positives. The contract-based arm recovers decisions on pairs the baseline left as timeouts, extending reach into harder cases. Every recovered decision is either a real divergence or a triageable false alarm. Notably, the system surfaced 9 pairs that ECBench mislabels as equivalent. These are pairs that are actually non-equivalent under the full equivalence notion, but the authors argue they are equivalent under the safety-preserving conditional equivalence targeted by the tool. This highlights the importance of matching the verification notion to the property of interest. The evaluation also confirms that the enforcement step is the binding gate. Once enforcement passes, replacement almost always follows. The LLM loop is efficient, and the partial contracts are sufficient. To summarize, this work establishes that sound, modular regression verification can be driven by a model checker's own counterexamples and a partial contract. The key contributions are: first, a soundness theorem for one-sided contracts that proves partial. Caller-sufficient abstractions are sufficient for regression equivalence. Second, an end-to-end system that infers these contracts automatically, reaching verification rates competitive with manual specification tools, while certifying a stronger safety property that includes runtime error freedom. Third, a semantic tightness comparator that demonstrates partial contracts capture nearly all attainable tightness, justifying the partial spec stopping point. The implications are significant. We can verify patches in large, long-lived C codebases without writing specifications by hand. We get soundness guarantees, we scale via modularity, and we leverage LLMs for inference while relying on formal verification for correctness. Future work points towards C++ contract inference, handling operator overloads and RAII, and regression verification across signature changes, where parameter reordering or type changes must be aligned relationally. This research provides a practical path forward for regression verification in the era of AI-assisted development. By focusing on what callers actually observe, we can verify changes efficiently, soundly, and at scale. If you're interested in the formal details, the definitions of safety-preserving conditional equivalence, the depth-bounded closure lemmas, and the SMT encodings used in Judge, I highly recommend reading the full paper. The methodology is rigorous, and the results are compelling. Thanks for watching. If you found this deep dive useful, check out the description for links to the paper and the tools mentioned. Let me know in the comments how you see partial specifications fitting into your verification workflow. Until next time, keep verifying,